Okay, so 187. Yeah, my mouse started not work, and that's why I had to stop last time. But anyway, now it's working, right? And now we can continue. So 187. First of all, yeah, I mean, I always do read the first few questions. I don't solve it, yeah, but I do read the first few questions. And the thing I noticed is that I have already solved this question. Yep, I've already solved this question once, not in this book, okay? But this question, I saw it in the exercise 5 of rotational dynamics from base booklets. And there I solved it, right? So the question is, a disk A of mass m sliding over a smooth horizontal surface with velocity v experiences a perfectly elastic collision with a smooth stationary wall at the point O. The angle between the motion direction of the disk and the normal of the wall is equal to alpha. Okay, right? The angle between the motion direction of the disk and the normal of the ball is alpha. Find the points relative to which the angular momentum m of the disk remains constant in this process. So the thing is, you got this p vector, right? That's the momentum imparted on this on this guy at this point, right? When the collision happens, only that has the capability to change the angular momentum because I mean something that's going in a straight line, that does not change its angular momentum as seen by a stationary point, right? But when you have this kind of impulsive acceleration, I mean that will change its angular momentum. So your momentum that was transferred to this particle, right? That should produce a torque. That means that the radius vector going from whatever particle you have to this point O, that radius cross this momentum, that should be zero for the angular momentum to remain constant. Now, what are such particles? The thing is, momentum is, I mean, yeah, that p vector applied on this guy is just in this direction completely, right? So normal to this surface, because of course no friction and anything. So that's just normal to the surface, and yeah, um, because of that, any vector that crossed with it gives zero must be collinear with this momentum vector, or you know, in the opposite direction of this, or with this. You get the idea, right? So that means all of the points which are on this normal line, right? Those work because going from those points to O, whatever that vector is, that's always going to be along the line of the momentum vector, and that means the angular momentum. So the impulsive change in the angular momentum, that thing is zero for all those points. And so A is, yeah, I just did A now. Okay, B, the magnitude of the increment of vector of a disk's angular momentum relative to point O, which is located in the plane of the disk's motion at the distance L from the point. So yeah, the momentum transfer to this thing must have been 2mvn, where vn is just the normal component of this velocity, right? Which is just going to be v cosine alpha, of course. So 2mv cosine alpha, that's the momentum, and this times L, that will give us our angular momentum's change, right? So the change in angular momentum is just going to be 2mv cosine theta times L. Yes, cosine alpha times L. Get the idea? So I'm gonna write down the things. All points on normal. Yes, and then B. It's going to be 2m v naught. Is this v naught or what? I don't know. It's like v, I think. Yeah, velocity v. So when I said velocity, it's actually just the speed. That's what they gave us, right? It's going to be v cosine alpha and that times L. That should do it. I should just say VL cosine alpha because I might mistake it for alpha L being the cosine, which is not the case. Right. So 187 done. Yes. And it's completely in the k hat direction. So yeah, but we just want the magnitude. So yeah, that's it. Next, 1.188. Okay. A small ball of mass m suspended from the ceiling at a point O by a thread of length L moves along. Oh, come on. Are you serious? Okay, I've seen this kind of question as well in that exercise. So, exercise 5 rotational dynamics case booklet. Okay, fine. A small ball of, yeah, I even suspected it must have been from Irodov because they are using weird notation, right? They too were using W and beta and who even uses these kind of things? And K for coefficient of friction, right? A small ball of mass m suspended from the ceiling at a point O by a thread of length L moves along a horizontal circle with a constant angular velocity omega. Related to which points does the angular momentum m of the ball remain constant? Okay, I've done this as well. The answer is all of the points that are on the central axis thing. Yeah, related to those, it remains constant. Find the magnitude of the increment of the velocity of force. Right, I'm not even going to do this thing. I already did this once and it's such an easy task. I won't even do this, right? So let's just skip that, 189. Right, so yeah, I mean the magnitude of increment of the vector of Paul's angular momentum related to the point O picked up during half a revolution. So just find the angular momentum initially, then finally, and then subtract. Right, you got this minus that. So I mean, finally, angular momentum is going to be like this. And initially, it was like this. So subtraction, you will just have this thing. So 2 times of whatever this component is, and then find the angular momentum is like not so hard. You just need to figure out what the velocity is. You already know the length from this point, right? Yeah, velocity is not that hard as well. Just find out what this actual radius is by using whatever this angle there. Oh yeah, and you have to figure out this angle by doing the force analysis on this guy. So you got mg in this direction, you got the centrifugal force, you got this tension, and from there you can figure out what this angle is. And once you have that, it's just a piece of cake. You can figure out what this radius is going to be, right? And yeah, then you know what this angle is, and then you can actually figure out the angular momentum because now you know the velocity and everything. So yeah, just not going to do it. 189. A ball of mass m falls down without initial velocity from. Oh come on, please no. Is this for real? They took this question as well. What? During a time of falling related to point O of it. Yeah, it's exactly the same question. What is going on? Of the reference frame, moving translation. Oh, come on. Are you serious? Eric, what? Please. What is this? Ah, this is so bad, you know? Okay, so O is this point, right? From here, I mean, as seen by the O point, right? It's moving translationally as well. So as seen by O, what's happening is that it had some initial, the ball has some initial velocity in this direction, and then it does this parabolic motion. It falls over here. What you want is just the increment of the ball's angular momentum vector picked up during the time of falling. So yes, just I mean, over here, the angular momentum must have been 0 because R vector is not there. It's just 0, right? Yeah, and then you just got this guy, that's a final condition. So we also do somewhere somewhat like this. You got this thing and this thing. What's the velocity? Yeah, it's moving translational velocity v. So you got v right here, gt right here. Figure out what time is. Come on. Do I really have to do it for you? Half gt square is equal to h. From here, figure out a time. You got this velocity. Just do it. Now that I have done half of the stuff myself, why not do the whole thing? This is so not good, you know. Okay, so from this equation you can figure out what t is. T is just going to be square root of 2h upon g. Just put that in there. You just get square root of 2gh. Nice. Once you know this, right, you got the velocity vector. You also have the r vector because hey, this thing is h, right? And then you got this, which is just v times t. Which guess what? You would know what the t is. So it's like v square root of 2h upon g. So now you know r vector. You know v vector. Let's say this thing is the positive x-axis, this thing is the positive y-axis. I know, unconventional, but whatever. So then our v vector is just v cross square root of 2gh, and our r vector is going to be v square root of 2h upon g, and then that comma h. Yes? Yeah. And then, yeah, just you need to figure out the angular momentum. So cross of this thing that equals r plus v, you just need to do m times that, and there you go, you got your angular momentum. I mean, since I've done half of this, just keep on going. So it's gonna be like what, m, and then this times this k hat. I know it's gonna be k hat everything, but yeah, it's the magnitude. This times that, it's going to be like what, v, that's okay, 2h common, okay, and then you got just 2h, so 2vh, and then minus of this times that, of course. Yeah, because j cross I is negative k, whatever. So that's gonna be negative vh, and that's gonna be like mvh, right? That's your thing. And I think in that, yeah, in that exercise as well, I just got mvh as our answer. So whatever. I didn't know this book was so popular that people are just getting, I mean, like copying questions for this. Yeah, I didn't think they would copy questions from books. I thought they were creating their own questions. Hey, whatever. 189. That's done. 190. A smooth horizontal disk rotates with a constant angular velocity omega about a stationary vertical axis, passing through its center. Horizontal disk. Okay, constant angular velocity omega about stationary axis passing through its center. The point O, right? At the moment t equal to 0, a disk is set in motion from that point with velocity v naught. Okay. Wait, what? What's this L thing? Related to point O in the reference frame, fixed to the. Wait, which disk? What do you mean by the disk? There are two disks, right? I think this is what they're talking about. Make sure that the angular momentum is caused by Coriolis force. Oh, come on, please don't do this. Coriolis force. But then, are you talking about this disk's reference frame? What are these people talking about? Okay, smooth horizontal disk. Let's read it this thing. Uh, the constant angular velocity omega about stationary vertical axis. Right, stationary vertical axis, passing through its center, the point O. A disk is set in motion from that point, so from O, of course, with a velocity v naught, right? Find the, what's this, m upon 2, m upon 2? What is it supposed to mean? What are you talking about? Oh, this is for some other question. Sorry, it's not involved in that. Sorry, sir. Sorry. But is this thing involved in this? Because they did talk about the disk being set in motion with velocity v naught, right? Some other disk. So at moment you to a disk, not the disk. So that means you are talking about some other disk, right? So maybe this part is for this 1.49 figure, and then wait. Oh, they didn't even talk about 1.49 anywhere, right? So they didn't refer to that. That means it's not. Oh, huh. Yeah, it's a completely different question. It's not related to these two figures anyway, right? So a smooth horizontal disk rotates with constant angular velocity omega over stationary vertical axis. So like this. Okay, you got a disk rotating about this. Right. Oh wait, I think they mean a large disk like that. Passing through its center. So the disk center, of course, it's supposed to be a large disk. At the point O. At the moment equal to 0, a disk is set in motion from that point. So, right, like this. Okay, with velocity v naught. And it's a smooth disk, right? Yeah. And this is just v naught as seen in the ground frame. Well, it doesn't matter, right? It doesn't matter if it's in ground frame or whatever. Because in this frame as well, yeah, it will work in both cases. So it's just v naught like that, and then yeah, it just goes like that. Cool. Find the angular momentum m of the disk related to the point O in the reference frame fixed to this disk. Right. Make sure that the angular momentum is caused by the Coriolis. I mean, what other thing do we know? It's, yeah, Coriolis force is all we can do in this reference frame, right? That's the most straightforward way of doing this. What other way could we use to make this happen? I don't know. Oh yeah, we can use the fact that when it okay, when this disk goes over here, its angular momentum, like according to this reference frame, it's now moving with omega in this direction, right? Yes. It was going in a straight line, yes, but now according to this guy, it's actually going like this. So yeah, its angular momentum is just I omega, which is mr squared omega, and then initially it was 0. So mr squared omega is um, the angular momentum that is got picked up. Okay, and this must also be equal to the angular momentum as what this thing thinks it's picked up, right? And that should be because of the Coriolis force, right? That's what this question is talking about. So we know in ground frame, it's not actually picking up any angular momentum, but it goes over here, and then as seen by the reference frame, it's going with omega. So just from initial to final, you can see the angular momentum change was the mr squared omega. But now we want to do this for every single point throughout this path, right? And maybe just figure out the path is no, okay, don't do that. Don't just figure out the path itself. That's not, yeah, don't do that. Anyway, one thing's for sure, like from this thing itself, you can clearly see that its distance from this axis is increasing at r dot is equal to v naught, right? This rate. And in this rotating frame as well, so the axes are also rotating now, right? These axes are also rotating. In this frame as well, your r dot is increasing by v naught because come on, the origin is the same. And the way distances are measured is the same, right? Distances, okay? I said distance is not displacements. So r dot is still it's just v naught in this case as well. Okay, that's good. And it's rotating with omega. So our Coriolis force will just be 2 m r dot omega. But it's supposed to be negative, I think. Yeah, it's supposed to be negative. Yeah. So this is the Coriolis force, which means the acceleration because of Coriolis force is just negative 2 r dot omega on this guy, and it's going with v naught in this. So yeah, according to this rotating frame, so if this is the origin, right, this guy was going with v naught like that, but it has this kind of thing. So it's in the tangential direction all of the times, right? That's important. It's in the tangential direction all of the times. Yeah, that's the tangential acceleration, which of course means like this upon r, which is just a 2r dot omega upon r is our angular acceleration. So negative is our so-called angular acceleration. Like just talk about the magnitude, in fact. So that's how this changes and everything, right? Understandable. And we can use the fact that tangential acceleration, the integral of that thing, is just going to be the final, the change in the tangential velocity, right? Yeah, we can use that fact. Of course, we can use that fact. So right now, so initially it's just v naught, like this particle is going with v naught radially away, right? But then there's this pseudo force acting on this guy. So what this guy will think, okay, is that it's rotating and then it ends up like, so this is the kind of path it took, yeah, with a constant angular acceleration and everything. Yeah, but also that's this v naught is in the direction. Oh yeah, the thing is like v naught is, wait a second, something's not right. So you got the Coriolis force, your alpha, what about that? No, something's not correct. What about your alpha? Oh wait, what? What was the actual pseudo force thing, the whole thing? So it was the Coriolis force, you got the centrifugal force, which is also there, right? Oh no. I don't want to do a full scale derivation for this thing. Oof. That's in the radial direction anyway, so I don't think that will actually create any kind of angular momentum. So you don't have to worry about that. Then there's the Coriolis force. There's also the Euler force, which deals with R alpha, right? So MR alpha, whatever. And yeah, well, that is there because it should be like Not. It should not be like that. It should be mr alpha naught. What am I doing? It's supposed to be omega naught over there. Yeah, that's how it's going to be. Omega naught, the angular velocity of this rotating frame as seen by the space frame, right? It's not the angular velocity of this, what do we call it? What am I doing? Something wrong, right? MR dot. It has to be like this has to be our Coriolis force, but there was also some other stuff which was like omega dash omega. Yeah, that's for the general case. Right, that was changing and whatnot. That was that from the Euler force? No, it must have been from. It was like a part of the Coriolis force, I think. Oh, I will have to see those iterations once again. We know what the value is, but then it's so. This is just unnecessary. What other tangential force there was? Of course, that other force, Euler force. Um, no, it was not good. That was not good. Come on. In planar, it's doing planar motion. That's for sure. Right. Just remember everything. Remember everything now. The total acceleration, the total pseudo acceleration was 2r naught omega naught, and then plus r alpha naught. All of this in the t hat direction, and then we had something in the r hat direction. So, wow, it's kind of complicated, isn't it? Wait, was this really just r dot omega naught or something else? This is a force, right? I mean, what? This is the acceleration, so it's got meter per. Uh oh. It's not. It's not the thing. R omega naught. That's not the thing. It should be R omega dash omega naught. Yeah. Damn it. I messed up, huh? Yeah, I messed up over there. Fine. So it's supposed to be R omega R dot, of course. And we got. Oh wait, so it's supposed to be R dot. Wait, then this might in fact be the. Yeah, this is actually the acceleration. Sorry. This is correct. Then what was this thing for? What was that? That was in this part, right? But we know that one of these terms was just a part of this Coriolis force, the total Coriolis force. Yeah. Man, something's just not correct. No, it was not the part. It's not a part of the centrifugal force. It's part of the Coriolis force. I just remember it. But then, what? It was 2 omega dash omega naught plus omega squared r, right? Yeah. Oh, it should be 2 omega dot omega naught, and then that times r, of course, and then plus r omega dash squared. Sorry, omega naught. What am I doing? Yeah, that's the angular velocity. So plus over there. If it is omega, then you just write 2 omega naught r minus r omega squared. So this omega is as seen by the space frame, but we will use this thing, of course. Yeah. So 2 omega dash, which is the angular velocity as seen in the rotating frame, omega naught r plus r omega naught squared minus all of this stuff. So how was it that this is like supposed to be actually a part of the Coriolis force? Damn, I don't remember it. I just don't remember it. Oh, it was not okay. Okay, now I understand what was going on. It was not just r dot omega. It was like 2 omega naught vectors, negative 2 omega naught vector cross v vector. That is actually what they call the Coriolis force, right? So that's why this was also part of this thing, and it's like in the r direction, of course. Yeah, now that's understandable, of course. So the only tangential thing that we have to deal with is this thing, because r alpha, so alpha naught is like 0, and then omega naught squared, that's not 0 anymore. It definitely has some omega dash as well. I mean, yeah. Wait, we know what omega is, right? So in the space frame, we know omega is just going to be 0. So we can write this thing as just like negative r omega naught squared. Yeah, r hat. So that's our pseudo force that we have to add while going from space frame to this frame. Yes? Yes. Huh, why is this okay, this turned out to be negative somehow. Uh, okay. Hmm. That's weird. Okay, like omega dash is just negative omega naught. That's why this works out. Understandable, no problem. Even though it's unnecessary, but still, okay, I understand this. Right. So this actually is the Coriolis force, actually. But the thing is, we don't use this. We instead just use this thing because we only care about the tangential component, right? We don't care about the radial component whatsoever. And it's like planar motion. So the best formula to use is just this thing. Okay, so there we go. 2r dot omega naught. That is the tangential acceleration that we are dealing with. Oh no, this mouse is okay. No, it's alive. Yes. So we just want the change in angular momentum. So according to the rotating frame, what's happening is that there's a radial force, so this times m, and then there's this tangential force, so this times m. So like negative 2mr dot omega naught. This tangential force is acting on it. Yes. So this times r. This must be the this must be the torque, of course. And what that means is you just integrate this guy just to time, and there we go. So you got the what is it? You got the angular momentum finally, because initially r was 0, so your angular momentum must have been 0. Yes. Okay. So just integration of this thing is going to be. I know it's like negative positive. Some sign convention is over here, but just ignore that, right? We'll only think what the magnitudes really. So yeah, m, and then you got 2r, and then dr upon dt. It's like okay, omega not m, and then dt, and then integration of all of this stuff. So right, which is just going to be integration of omega naught m, and then dr upon dt times dt is like dr, and then 2r dr is just d of r squared. So this will be omega naught m times r squared, or I should say delta r squared, but then r initially was 0, so it's going to be in the end just omega naught m times r squared, which is that's for 189. So we are doing 190, right? Yeah. So this is exactly what we got previously as well, mr squared omega naught, right? Yeah. So there we go. Oh, and now this negative makes sense somehow. Okay. Okay. Understandable. So yes. So yeah, we did make sure that this angular momentum is caused by the Coriolis force as seen in a rotating frame, although this is a very inefficient way of actually calculating the thing. Right? Why take all of that trouble? Yeah. Oh, okay, wait. I think this 1.49 is talking about this, because look at it. Like, okay, this complete surface is like rotating, and then you got this thing which is going in linear motion or something. Um, yeah, whatever. That's how it is. So there we go. Oh, and also you had to find the angular momentum of the disk related to. So as a function of time. Wait, what? Uh, oh no, as a function of time, huh? Hey, no problem. So r square is just like it can be found out easily because r dot is just v naught all of the time, right? Yeah, in the space frame, we just know r dot is v naught. Although you have this stuff happening actually, so it's like negative r omega naught squared force in that direction. That pseudo force is there somehow. And then it's also, oh yeah, so that is required to keep it rotating like that. And Fine, it will manage itself as well. The thing is, r dot is v naught, so r will just be v naught t. So there we go. It as a function of time is as seen in a rotating frame. It will just be omega naught m times v naught squared times t squared, right? Okay, next question. 191. A particle moves along a closed trajectory in the central field of force where the particle's potential is given by kr squared. R is r is the distance of the particle from the center O of the field. Find the mass of the particle if its minimum distance from the point O equals r1 and its velocity at the farthest point from O equals v2. Wait, just I'll close the window. Right, it's not helping much, but whatever. Okay, closed trajectory in a central field of force. Oh, so it's like, I don't know, some kind of orbit where a particle's potential energy is kr squared. Oh, okay. R is the distance of the particle from the center O of the field. Distance of the particle of the field. Okay. Find the mass of the particle if its minimum distance from the wait. It's kr squared. Then if it moves tangentially somehow, right? So, the divergence of this thing is okay. I know you guys don't know about this thing. How do I tell you about this? So I made a video on the divergence and curl stuff, mainly the curl, but it can also be like applied to divergence and stuff. So in cylindrical coordinates, right? We can use that fact over here and say that okay, the tangential forces are just zero. It's completely in the radial direction, right? Because yeah, that's like obvious from this fact. Even if you move like through a circle, it won't do anything. Through a circle, it won't do, of course. If you move tangentially, right, your potential energy is not changing, but you are moving though. So potential is not changing as you move tangentially. That just means like okay, the tangential forces must be zero. That's all you can say really, because your velocity must remain constant as you move like that. So yeah, that means there's no force in the tangential direction, because yeah, that's all it can possibly mean. There we go, right? So it's just the radial direction. Find the mass of the particle if its minimum distance from the point O equals r1, its velocity at the farthest point from O equals v2. Minimum distance from the point O is r1 and its velocity at the point farthest from O is v2. Oh, so at farthest from O, it's going to be the least velocity and whatever. It's I wish it was something like gravitation. I could have applied all those formulas that I know, but okay, it's different, right? But still, once again, you can just do angular momentum conservation and energy conservation to get this thing, right? Yeah. So you want to find the mass of the particle, huh? Oof. Okay. Minimum distance from the point O equals r. Hey, so we can of course use, I mean, something similar to Kepler's law about, I mean, area being swept in some amount of time, right? You can apply the same kind of thing over here as well. Yeah, but we don't know what shape this is in, so no thanks. This one do. So now what do? We don't know what the shape is. Just know nearest distance is r1 and the least velocity is v2. Okay, let's just write down our things. R1 V1 is equal to R2 V2. Wait. Yeah, there must be no radial velocity, right? Because the thing is like, if this is the least distance, then what must happen is that dr upon dt at R1, that must be equal to 0. And as well at R2, it should be 0. What that means is like, there's no radial velocity. That's the thing, right? There's no radial velocity, which means that velocities are just perpendicular to the radius. And in that case, you can just write this equation. So by angular momentum conservation. Okay. And also energy conservation tells us that what's going to happen is that k r1 squared plus half m v1 squared is equal to k r2 squared plus half m v2 squared. So our main aim is just to figure out what m is. Okay, fine. So you just got like, okay, m upon 2 is equal to k times of r2 squared minus r1 squared upon v1 squared minus v2 squared. Now, how do I mean, somehow solve this? Think about it. What we can do is just, I mean, we know what R1 is. We also know what V2 is. So we can say, okay, V1 is equal to R2, V2 upon R1. If you put that in there, what you get? Just get K R2 squared minus R1 squared, and then V2, sorry. And V1 is just going to be R2, V2 upon R1, that thing squared. So it's going to be like, okay, V2 squared common. You just got R2 upon R1 squared, like R2 squared minus R1 squared, and that thing upon R1 squared. Boom. Cancels. Perfect, right? It's going to be k times r1 squared upon v2 squared. So somehow, even though we didn't actually write down three equations, wait, you would just need what? Yeah, you would need one for this mass, right? That's one variable. You got these two other variables, so you would need another equation to actually, I mean, definitely solve this, but it somehow solved itself. Yeah. Fine, fine. So you got to think, mass is now known. So the mass must just be 2k r1 squared upon v2 squared. Cool. Let's go to 192. Okay. A small ball is suspended from a point O by a light thread of length L. Then the ball is drawn aside so that the thread deviates to an angle theta from the vertical. And set in motion in horizontal direction. What? Oh, okay. So, like a conical pendulum. Okay. At right angles to the vertical plane in which the thread is located. Fine. Right. What is the initial velocity that has to be imparted so that the ball so that it could deviate through maximum angle pi upon 2 in the process of motion? Wait, what? They didn't give us a figure. Huh. Thread deviates to an angle theta, okay, from the vertical. So like this is angle theta, and that in motion in a horizontal direction. This is the horizontal direction, right? What is the initial velocity that has to be imparted? So what's our v naught such that it could deviate through the maximum angle pi upon 2 in the process? Wait, what? Can deviate through the maximum angle pi upon 2. What do you mean by it? The ball, right? Or what? Wait, I don't understand what's happening. What kind of motion is this doing? What I'm suspecting is that it's doing some kind of elliptical motion like this. Might be. And then, no, but in that case, the thread will, oh god, no. I mean, okay, this might be happening that like this thread is not, it's going to be some kind of cone. Yeah, no, a cone would not be the thing. But then this length must be different. This angle cannot be theta, of course. It's going to deviate from theta, so maybe it's like theta minus pi upon 2. Like this complete thing is pi upon 2. These are right angles. Of course, the base is like this, so right, like this might be the base of the cone, something like this. Yeah, this is how the trajectory might be. And then this angle theta is actually more than the half of the angle, which is like pi upon 4. Okay. because it's gonna deviate by 90 degrees, right? So then this must be 90 degrees. What is this? Minimum velocity is just that this deviates by that. What happens if we give it a higher velocity? Does that change anything? What does it change though? Oh, okay, and maximum angle of 5.2. Okay, so at the, oh yeah, okay, that's understandable. Fine. So how do we solve this? Uh, Angular momentum conservation? No. The thing is, like, gravity is. Okay, gravity is just messing up everything. It's not making angular conservation work. Something that's like somehow r vector would be always along gravity. No, that just cannot happen. So give up that hope. Uh, One thing you know is that this length of the string is always a constant. That means this is going in a cone. So this path that it traces out, it must be some kind of conic section, of course. Yes, that's what we can say for sure. It's going to be some kind of conic section. Uh, yeah, well, this radius not necessarily going to be constant, right? Or is it from this particular? Okay, what do I do now? Uh, there's this gravity force acting which causes angular momentum to changing. Yes. I don't understand. What can I do with it? Okay, that's one thing. And then what? Uh, Energy conservation. Of course, I'm like, okay, you can do that for sure. Yes. It's complicated, huh? I don't understand how it's deviating, but I'm just making a guess that it's deviating like I've shown. The process of the motion. Angular momentum changes, right? That's the problem. Just if angular momentum didn't change, that's not going to happen anytime soon. There's this thought. So about this point, of course, angular momentum is going to change all of the time, right? Actually, in any point, the angular momentum is going to change. So now, how do we deal with it? Energy conservation, sure. The work energy theorem works because the tension is not doing any work, right? It's just moving perpendicular to tension. So yeah, that works out. Right now the string is inaccessible, so dr upon dt times t, that's the power given by the tension, which is 0, right? Sorry. So that's not here. And okay, so work, I mean energy conservation will work, of course. So if this is theta, okay, this is angle theta, this is going to be 90 minus theta, because this complete angle is going to be 90. So yeah, right, so that this deviation, so going from there to there, is now 90 degree. Or do we mean like the velocity deviates by pi upon 2? What? How could that be happening? It's sent into motion in a horizontal direction at right angles to the vertical plane, right? So it must be something either like a conical pendulum or like this thing, whatever is happening over here. So yeah, that's what it is. Uh, what do you mean by deviation here? Do we mean the deviation of the velocity or of the angle or what? If this is the angle, it might be easier. If it's the velocity, oh god, that's just, yeah, not interested in doing that. Nope. Okay, so you got this change in the height, of course, because this is going to be L, this is going to be L. So L cosine of this is like L sine of theta, and this is like L cosine of theta. So L sine theta minus cosine theta. It's our h part. So mg times this thing. This is going to be equal to our change in velocity, which is like half m. This is like u, initial velocity u. So half m v squared minus u squared. That's one thing. Okay. And other things, what can we use? We can always use the fact that you got angular momentum change, and what's the torque? What's the torque about this point? What am I doing? It's like, wait a second. It's not a cone necessarily. It's a part of a sphere. Oh no. Right, it's a part of the sphere, you see, because this distance from a particular point is constant, it might actually go like this. It not necessarily need to be a cone. It could also be a sphere. I mean, okay, something on a sphere, right? Yeah, right. It might not even be a plane in the first place. Oh, what is this? You just write down some equation that will give us clarity. So, if at any point your angle made with the vertical is theta, right, then you got this. I'm gonna use something else. Then theta's like phi. If this is phi, then what do you have? Um, so if this is phi, you got gravity over here, mg, and then you got this length L. You got some angular momentum. We don't care about it. We just care about the torque. So the torque is in this direction. Wait, what? Yeah, r cross f. That's why this thing. Okay. Angular velocity, angular momentum is in fact like this. Okay. And what is this torque? This won't help. And oh, it's always in the tangential direction. That's also like I think important. Okay, it's always in the tangential direction. Nice. And then what? How does it actually help us? Can we write down a vector equation for this thing? Sure, maybe. Now my brain is just not working anymore. Yeah, you will have to do like proper 3D analysis of this thing. So it's not something I can just directly do. Environmental conservation won't work right away. Let's see. We need this torque. What? So like, okay, mg phi right here, right? So mg sine phi times L. Okay, that's our magnitude of the torque. But then its direction is in this kind of thing. So phasors might work, you know. Yeah, it could. It's always going to be tangential. That's for sure. Somehow this should give us like somehow it should be integratable as a vector. How do we integrate it to? Mg sine phi times L. What's L sine phi? L sine phi is just this thing, right? So it's like a constant times whatever this value is, right? And then we're trying to integrate this thing. So it's like, okay, mgr integration of that thing. So wait, what? Oh, this times dt as well. So r dt, we want to integrate this thing. We don't know how r behaves as a function of time though. So yeah, how would this work? It won't. It just won't. But we have to integrate with time. Otherwise, how are we going to do anything? Okay, this is it. I think something's missing. I just don't know some other equation. So yeah, I will have to stop now. See you guys in the next video. Bye.